Hello everyone, welcome back to the online lecture series on fluid mechanics. Today is the third lecture of fluid mechanics and today we are going to discuss a new topic which is the continuum hypothesis in fluid mechanics. In the last class we have seen the two approaches of analyzing the mechanical behavior of fluids, namely first was the microscopic approach and the second was the macroscopic approach, and we have learned that how we are going to use this microscopic approach in case of fluid mechanics. However, the microscopic approach also have certain constants associated with it. Let us see what are those constants. Let us say that let us assume that we are interested in computing the density of the fluid. Now the density of the fluid is defined as mass per unit volume. The mass per unit volume. Now, how are we going to define the mass, or how are we going to compute the mass of the given volume of fluid? The mass may be calculated as the number of molecules in that elemental volume into the molecular mass. So if we know the number of molecules for a given elemental volume, we can easily calculate the mass of the fluid, and if we divide it by volume, we will get density. That is quite simple, fundamental. So, but in case of fluids, what happens? Fluids are constantly in motion, that too in a random manner. So, if we take a very small elemental volume, the number of molecules in that elemental volume will be less. If the number of molecules in that elemental volume will be less, we will get a lesser mass and hence a lesser density. If we consider a greater elemental volume, the number of molecules will be more, as it is quite obvious, and we will get a larger mass and hence the density of the fluid will be large. But how is that possible? Because for a given fluid we have a specific density. So this is not true. What does that means? It means that there must be a limiting volume above which the number of molecules that has to be taken for a given fluid is sufficient enough to give a clear picture of the density of the fluids. Now, for that case, we have a hypothesis which is known as continuum hypothesis. Now, let us see what this continuum hypothesis means. The word continuum is actually made up of two words. First is continuous and the second word is medium. So joining these two words, continuous plus medium, gives us the word continuum. As it is quite obvious that what we are going to do in hypothesis, we will approximate the fluid to be a continuous medium. It means the continuum hypothesis is a kind of idealization in which the distribution of mass within the fluid will be assumed continuous. In simpler terms, you can say that suppose the figure here, what what does this represents? This represents the actual conglomeration of molecules within the fluid with spaces or voids in between. So let us write this. This is the actual conglomeration or aggregation of molecules with empty spaces also known as voids in between. As we have already discussed the certain constants of microscopic approach, that if we consider a very small elemental volume, the number of molecules will be less, and if we assume if we take a larger amount of volume, the number of molecules will be large, and hence we will get a different value of the property which we have used, that is density. But here in continuum hypothesis, what we are going to do, we define that within a limiting volume, we'll take a limiting volume, and within that limiting volume we will say that instead of the actual conglomeration of molecules with empty spaces, we will have a continuous distribution of mass within the system with no empty spaces in between. So instead of the actual conglomeration, we will have a continuous distribution. So this is a continuous distribution of mass. That means there are no empty spaces. Now, what is the use of this approximation? The use is that now we can define the properties of fluid at each and every point of the given volume, or rather in technical terms you can say that we can define the properties to be a continuous functions of space and time. So what we do here, we consider the fluid to be a continuous distribution of, there will be a continuous distribution of mass, and there are no empty spaces. Now, of course, this is valid under certain conditions. The condition which we have already discussed is the limiting volume, and this the validation of this approximation, this is done by using a non-dimensional parameter which is known as Knudsen number. So here we are going to take two cases, two important conditions. That first is the scale of interest, say L. Suppose the scale of interest is L and the mean free path of the molecules is small l. So if we take the mean free path as small l and the scale of interest or the characteristic scale as capital L, we define the Knudsen number, which is represented as Kn as small l upon capital L. So if the Knudsen number, if the value of the Knudsen number is less than 0.01, then our continuum hypothesis is valid. Continuum is valid. If the Knudsen number is greater than 0.01, then it is not valid. Of course, there are values in between these values. If the Knudsen number lies between 0.01 and 0.1, then the flow is known as sleep flow. If the Knudsen number lies between 0.1 and 10, then the flow will be known as transition flow. And if the Knudsen number value is greater than 10, then we will say that there is a free molecular flow. Now, what is the implication of this? That this hypothesis allows us to consider the fluid properties as continuous functions of space and time. That means the properties can be expressed as continuous functions of space and times, or the continuous functions of state variables. And each fluid property is in a continuum will have a unique value at each point in the space. Or we can, or in a more simpler terms, you can say that we can define the properties as point functions. So next we are going to define the different physical properties of fluids, starting with the mass density.